Okay, let's just dive right into this. Welcome to today's Explainer. We're going to treat the discovery of atomic structure not as some dry, dusty science lecture, but really as one of the greatest historical detective stories ever told. For centuries, we thought the atom was the absolute end of the line, the unbreakable, indivisible building block of all matter. But as scientists started peeling back the layers, they realized they were staring at this entire microscopic universe filled with hidden suspects, invisible forces, and just mind-bending rules.
To truly appreciate this mystery, we first need to kinda reset our brains a bit. When you look at your desk, your hands, or the screen right in front of you, it all feels incredibly solid, right? But what if I told you that reality is mostly an illusion of scale? Let's take a journey to the very core of an atom and completely challenge your perception of solid matter. Do you actually know how small the center, the nucleus, really is compared to the rest of the atom?
Well, to put this into perspective, imagine the nucleus is a tiny ball sitting right in front of you. If that ball were the nucleus, the outer edge of the atom wouldn't be just across the room. Actually, scratch that. It wouldn't even be down the street. The atom's outer boundary would be a massive 5 kilometers away in every single direction. Think about that for a second. The vast, overwhelming majority of an atom is just completely empty space, with these tiny electrons zipping around the void.
So how did we figure all this out? Well, our agenda for this explainer breaks down into 4 parts. Number 1, the clues. Number 2, the atomic sketch. Number 3, the identification. And number 4, invisible waves. Let's get right to the investigation.
Section 1. The clues. Finding subatomic particles.
So this is where scientists first realized the atom wasn't just a solid, empty black box, but a container actually hiding smaller, distinct pieces. Back in the 1850s, scientists like Michael Faraday started experimenting with passing electricity through partially evacuated glass tubes, and they noticed this strange glow originating from the negative end, or the cathode, moving toward the positive end, the anode. J.J. Thomson later studied these cathode rays and found they traveled in straight lines, but could be deflected toward positive electrical fields. Because opposite charges attract, Thomson realized these weren't just rays of light, they were a stream of negatively charged particles. And the wild part? It literally didn't matter what gas or metal was in the tube. These identical negative particles were in everything. He had discovered the electron.
To figure out exactly what these electrons were, Thomson studied how they moved when exposed to electric and magnetic fields. Think of it like a kid, let's call him Alec, standing in a hallway with 2 doors, the game zone and the library. If we give Alec a push, where does he go? Well, it depends on 3 things. First, the magnitude of charge. Basically, this is Alec's interest level. If he loves games, he's going to turn sharply toward the game zone. Second, the mass of the particle. If Alec is a tiny, lightweight kid, a small push will send him flying into the room. But if he's a heavy-set linebacker, that exact same push won't deflect him much at all. And finally, the strength of the field, which is just how hard we're pushing him. By measuring these exact deflections, Thomson couldn't quite find the exact mass or charge yet, but he brilliantly calculated the precise ratio between them.
The next big breakthrough came from an American physicist named R.A. Millikan and his incredibly famous oil drop experiment. By suspending tiny, electrically charged droplets of oil between metal plates, he found that the charge on any drop was always a simple multiple of a single, unbelievably tiny base number, negative 1.6 times 10 to the power of negative 19 coulombs. By combining this exact charge with Thomson's ratio, the detectives finally had the exact mass of their suspect. The electron was real, and it was unbelievably light.
But wait a minute, atoms are electrically neutral overall, right? So if there's a negative electron, there has to be a positive counterclue to balance the whole thing out. Scientists modified the glass tube, putting holes in the cathode this time. And sure enough, they found rays traveling in the exact opposite direction, toward the negative side. These were called canal rays. However, unlike electrons, the mass and charge of these positive particles completely depended on the gas inside the tube. By using the lightest gas, hydrogen, they isolated the smallest, lightest possible positive particle. They named it the proton.
Okay, let's quickly summarize the profiles of our microscopic suspects here. We've got the lightweight, negatively charged electron discovered by Thomson. We have the much heavier, positively charged proton. And finally, rounding out the table, in 1932, a scientist named Chadwick discovered the neutron, a particle with roughly the exact same mass as a proton, but entirely neutral, carrying literally 0 charge. Our suspect lineup was complete.
Section 2. The atomic sketch, shaping the model. Now that the detectives had their pieces, they had to figure out how they fit together to build an actual atom.
J.J. Thomson initially proposed a model that looked kind of like a watermelon, or a plum pudding. He thought the atom was this big sphere of positive charge, with negative electrons embedded inside it like watermelon seeds. But then, a scientist named Ernest Rutherford came along and proposed something entirely different, a solar system model, where the positive charge was crammed into a tiny center, with electrons orbiting it like planets around the sun.
To prove which sketch was correct, Rutherford set up this absolutely ingenious experiment. Step 1. He took a radioactive source that fired heavy, positively charged alpha particles at incredibly high speeds. Step 2. He aimed these particles at a sheet of gold foil, pounded so exceptionally thin it was only about 1,000 atoms thick. And Step 3. He surrounded the foil with a fluorescent screen that would flash every single time an alpha particle hit it, allowing him to track their exact paths.
Now, if the plum pudding model was right, those heavy alpha particles should have blasted straight through the soft positive sphere with almost no deviation. But the results were shocking. Most particles did pass straight through, confirming that the atom is mostly completely empty space. Some deflected at slight angles, meaning they brushed past a highly concentrated positive charge that pushed them away. But a very small fraction did the unthinkable. They bounced straight back. Rutherford later said it was literally like firing a 15-inch naval shell at a piece of tissue paper and having it bounce back and hit you. So the crucial takeaway is this: all the positive charge and almost all the mass is packed into an unbelievably dense, tiny core. The nucleus was discovered.
Section 3. The identification, atomic IDs. With the solar system model established, scientists needed a way to formally categorize these elements. It turns out the number of protons acts as the ultimate ID tag for any element. This is called the atomic number, denoted by the letter Z. If you have 8 protons, you are always, without a doubt, oxygen. Change the protons, you literally change the element. Meanwhile, the mass number, denoted by A, is simply the total weight of the nucleus, so the protons plus the neutrons combined.
But nature loves to throw in a plot twist, doesn't it? Enter isotopes. These are versions of the exact same element, meaning they have the exact same number of protons, but they have a different number of neutrons, which changes their overall weight. Hydrogen, for example, has 3 isotopes: protium, deuterium, and tritium. Carbon has carbon-12 and the heavier carbon-14. Chemically, they act identically, but physically they are different, which is exactly why some isotopes are incredibly useful in things like nuclear reactors or medical treatments.
And just to keep us on our toes, we also have isobars. This is the exact reverse scenario. These are completely different elements, different atomic numbers, different chemical properties that just happen to weigh the exact same. For example, argon has 18 protons and calcium has 20 protons, but because of their varying neutron counts, both of their mass numbers total exactly 40. They just share a weight class.
Section 4. Invisible waves, the next mystery. Because as brilliant as Rutherford's solar system model was, it had a massive, fatal flaw. A physicist named Maxwell had already proven that whenever a charged particle accelerates, it emits electromagnetic radiation, which means it's losing energy. Well, an electron orbiting a nucleus in a circle is constantly accelerating. According to the laws of physics at the time, that orbiting electron should bleed energy, spiral inward, and crash right into the positive nucleus in a fraction of a second. The atom should instantly collapse. But since you and I are sitting here in a completely stable universe, that obviously doesn't happen. To solve this, scientists realized they had to understand the dual nature of these invisible emitted waves.
Let's define exactly what we are dealing with when we talk about electromagnetic radiation. Imagine a wave traveling through space. The first vital parameter is the wavelength, represented by the Greek letter lambda. This is simply the physical distance between one peak, or crest, of the wave and the very next peak.
This builds directly into our second parameter, frequency, represented by nu. This is how many of those wave cycles pass a specific point in 1 second. There is a strict inverse relationship here. If your wave is really stretched out with a long wavelength, fewer of them will pass by each second, meaning you have a low frequency. But if your wave is tightly squished together with a short wavelength, many will pass by, giving you a high frequency.
This inverse relationship gives us the entire electromagnetic spectrum. On one end, you have radio waves. These have massive wavelengths, sometimes as big as buildings, and very low frequencies. That's exactly why we use them for FM stations. Right in the middle, we have the tiny sliver of waves that our eyes can actually see, visible light. But as the wavelengths get smaller and the frequency gets higher, the waves gain incredible penetrating energy. X-rays have wavelengths so tiny they're literally the size of atoms, allowing them to pass right through our soft tissue so doctors can see our bones. And gamma rays are even smaller and more energetic.
Understanding these waves and how light can act as both a wave and a particle was the key that ultimately fixed the atomic model, eventually leading us straight into quantum mechanics. But as we wrap up this explainer, I want to leave you with this final mind-bending thought. The screen you are looking at right now, the chair you are sitting on, and your own body are all made of atoms. And as we've learned today, those atoms are almost entirely empty space, held together by tiny specks of matter and invisible forces. So, if we are 99.999% empty space, why does the universe feel so incredibly solid? Keep thinking about that one. Thanks for joining me on this microscopic detective journey.